Good morning. My name is Kostas Panos, and I'm proud to be the chair of this department, which, by my accounting and by many people's accounting, is one of the best on the planet, and that's not exaggeration. So one of my most pleasant duties is to brag about our department, the quality of our people. So I would like to start by thanking the people who put this event together. Rachel Schaefer, who sits over here, Gabe Chang, Miyoko Tsubamoto, who is probably out there handling, she's there taking pictures, who worked with Kate Raleigh to put this event together and did a great job. I would also like to acknowledge Professor Dave Patterson, known to all of you, I hope, who is the director of our Industrial Liaisons Office and is truly the architect of today's program. So I hope you'll enjoy it. So today is my duty to be the MC of this event. And this event is all about the future. We are in the crystal ball business, and we're pretty good at it. I hope you'll find it interesting. And this event is our annual opportunity to talk to our friends from industry, academia, and the press. So, as you noticed, those of you who have been in this event a few times who have had to move to a new venture to accommodate the growth. This event has been growing by about 20% a year for the last 5 years. So now, today, we're expecting about 500 people to show up, and the weather may be delayed a few of them. I'm sure they're going to be trickling in. However, before we start to that, I have another pleasant duty to tend to, which is the annual recognition of the distinguished alumni of our department. Every year, we give this recognition to a few people, some from the electrical engineering division, some from the computer science division. And these people receive the recognition because they have achieved distinction. And doing that among a group of overachievers is quite an accomplishment. So I would like to start, and if I can find this presentation, by recognizing the 2011 Electrical Engineering Distinguished Alumni. And I would like to start with Stephen Boyd, who is Samsung Professor in the School of Engineering at Stanford. I would like to say a few things about Steve, and I have not memorized them all. So Steve got his PhD from Berkeley, from our department in 1985. He worked under the direction of Professor Charles Desor and Leon Chua. And he's currently the Samsung Professor at the School of Engineering at Stanford, a place, by the way, who employs quite a few of our graduates. His current research focus is on convex optimization applications in control, signal processing, and circuit design. In 1992, he received the American Automatic Control Council Donald P. Ekman Award, which is given every year for the greatest contribution to the field of control engineering by someone under the age of 35. So you can do the math, see how old he is. In 2003, he received the AACC Ragazzini Education Award for contributions to control education. And another one of his distinctions is his website. His website makes available past papers, books, software, lecture notes, and selected lecture videos, and it is visited more than 1.3 million times a year, not counting access to iTunes U, Stanford Engineering Everywhere, or MIT OpenCourseWare, each of which includes courses developed and delivered by Steve. Steve, I would like to congratulate you for this distinction, and I would like to say that your citation reads, "For distinction and excellence in research and education." Thank you very much. I would like to acknowledge the second recipient of the 2011 E Distinguished Alumni Award, Dr. Jin-Fu Chang. Dr. Chang is unable to attend today's event, and when I read you his bio, you probably understand why. He received his PhD from our department in 1977, and he's currently serving as a cabinet minister in Taiwan. So he's busy with affairs of state. He spent much of his career as a faculty member at the National Taiwan University, becoming the director of the Science and Technology Advisory Office for the Ministry of Education from 1987 to 1990. In 1996, he was appointed vice chairman of the National Science Council of Taiwan and stayed in this post until May 2000. He was the president of National Tainan University from 2000 to 2008 and became a cabinet minister in 2008. From 2009 to 2010, He was the governor of Taiwan province, and his citation reads, "For dedicated and distinguished public service through technical leadership." I would like now to introduce Professor David Kaller. Professor David Kaller is known to most of you for his own accomplishments. He's also the Associate Chair of the Department and the Chair of the Computer Science Division, and he's going to introduce the recipients of the Computer Science Distinguished Alumni Award. David.
Great, thank you very much. So today we get to speak to a couple of our distinguished alumni that have been out changing the world. I see a lot of other distinguished alumni here. From a computer science point of view, this has been a pretty good couple of weeks in terms of changing the world. I guess we demonstrated the power of information technology over well-established autocracies, and we won Jeopardy. So our first of our recipients today is maybe not the only computer science alumni to win an Academy Award, but certainly the first, and is setting a high bar for the rest of the alumni to follow, and that's Tony DeRose. And if I can read just a little bit. So Tony is currently senior scientist and head of research at Pixar Animation Studios, hence part of the Academy Award. Received his PhD in 1985, early in our computer graphics program with Professor Barsky. Worked closely with Ed Catmull in those years, was a faculty member then at the University of Washington, and personally I can remember visiting there in 1989. It was, Tony's lab was absolutely a big part of the spark of University of Washington. And fortunately, Ed did his work and pulled Tony back into the Bay Area in the case of Pixar. And a key part of that transition in 1998 was his contributions to the Oscar-winning short film Jerry's Game, and in 1999 received the ACM SIGGRAPH Computer Graphics Achievement Award, and in 2006 the Scientific and Technical Academy Award for his work on surface representations, which he calls Pixarian physics, making things look as real as they really aren't. Tony, so congratulations for our 2011 Distinguished Alumni. And this one reads, "In recognition of foundational advances in computer graphics and animation." Thank you, Tony. And it's a hell of a lot of fun. Our other recipient this year is Professor Benjamin Wah, to get the rest of my notes. And as you can see, our relationship to Asia is a really critical part of the success of our department. And that's been a great deal of Professor Wah's focus throughout his career. He so after receiving his PhD at Berkeley in 1979 with Professor Ramamurthy, is here with us today, thank you. Joined the faculty at University of Illinois Urbana-Champaign in 1985, was the Franklin Woltage Endowed Professor of Electrical Engineering and Computer Science there, in areas of nonlinear programming, multimedia signal processing, and artificial intelligence. Numerous international awards, and much of his career really has been focused on the translation of computer science technology in both directions with respect to the United States and Asia. Currently, he is carrying that out, serving as provost of the Chinese University in Hong Kong. Professor Wah. This reads, "For leadership in the development of international programs in computer science and engineering." Thank you very much.
Thank you. I would like to congratulate our recipients and also welcome all the past recipients who might be attending BEARS today. So today's program is all about the future. I would like to go back, if I may, to the outline of this program, and I hope that's the right thing to do. Okay. It consists of 4 presentations, 4 keynote presentations, and a panel discussion. And the first presentation is about big data. The people working on it found a very catchy name for it, the AMP Lab. AMP stands for Algorithms, Machines, and People. And the presenter is going to be Professor Ian Stoica. I would like to say a few words about Ian. Ian, of course, is a professor, as an associate professor of electrical engineering and computer sciences in our department. He's also the acting chief technology officer of Conviva Networks. And he was awarded the Presidential Early Career Award for scientists and engineers in 2002, the Alfred P. Sloan Fellowship in 2003, and the Connext Rising Star Award in 2007. So I would like to welcome Ian. Yeah. So let me see. If I can find this. Is that it? Okay. No, that's not. Is that it?
No.
Go to the desktop.
Go to the desktop. You guys take it.
It's on desktop.
Oops. So good morning, and thanks for all for coming here. I know that some of you come from afar. So today, my name is Ian Stoica, and today I'm going to talk about the Berkeley View on big data. And so today we are reading on a regular basis, both in the popular and the scientific press, about the data deluge which confronts many organizations and companies. So for instance, Facebook collects every day around 130 terabytes user logs. In addition, its users upload over 80 million of pictures, which amounts between 200 and 400 terabytes per day. Google processes more than 25 petabytes of data per day, and the Large Hadron Collider in Switzerland can generate as much as 1 petabyte of data per second. In a recent IDC report, it is estimated that in 2010 alone, the humanity created 1 zettabyte of new information. And this information increases at a rate of 60%, has increased over the past 4 years. And this data is only going to become bigger and bigger. So there are more and more devices today connected to the internet to generate more and more data. The obvious examples are cameras, which generate large pictures and videos, are sensor networks, which monitor everything, starting with the energy consumption in buildings, the human, emotional and physical activity, and the structural integrity of buildings and bridges. Of course, there are phones, there are tablets, game consoles. Every game console now is connected to the internet, generating more and more data, personal training devices. In addition, there are more and more people connected to the internet. So it's an astounding statistic is that today there are more than 3.6 billion of phones in the world. And more wireless technologies and networks are deployed not only in industrialized countries, but also in third world countries. Finally, the storage becomes cheaper and cheaper. And the reduction in the cost of the storage encourages, incentivizes people to store and more and more. So why do you want to store more and more? Well, one of the fundamental reasons is that many times you do not know what questions you are going to ask based on the data you are collecting. Okay? On the flip side, it's hard to decide once you have the data, store the data, it's hard to decide what you are going to delete. The deletion is a thankless decision. People know only when you are wrong. So case in point, that recently, the scientists at the Climate Research Unit, they admitted that they threw away key data used in global warming calculation. Now, in a hot debate like global warming, you can imagine the repercussion of this throwing away this kind of data. And putting everything together, the stored data today grows at a much faster pace than the gigabytes per dollar. So this means, that we are really facing a big challenge. So now, what is really this big data? So I'm going to try to a more precise definition. So in this talk by big data, I'm going to, what I mean is that data that is expensive to manage and hard to extract the value from it. Okay? And one important thing to note is that you do not need to be a big organization like Google or Yahoo and so forth to have a big data problem. So indeed, many smaller organizations confront with inadequate tools to analyze the data, so therefore it's hard to extract value from the data they have. And they are in a situation in which the data management may dominate their infrastructure cost. So that's a big data problem for this organization. So big data doesn't come cheap, despite the fact that the cost is continuously dropping. The data is, again, grows at a much faster pace. So storing and managing today 1 petabyte of data costs anywhere between 500 and 1 million per year. And just for the context, Facebook collects or gets as much as 200 petabytes a year. Let me take another example of a smaller company, like a typical cloud-based service startup. And here I'm going to talk about Conviva, with which I was involved for the past few years. So as a part of the service, Conviva collects logs. And right now, it has 1 petabyte storage capacity for these logs. And here on the right-hand side, in this plot with red, is a cost of the storage as a part of the total infrastructure, as a fraction of the total infrastructure cost. So two things worth mentioning here. So first, as a year, every year, except for this 2008, the cost of the storage as a fraction of the total cost has increased. The second point is that today, it's more than half of the total infrastructure cost. It's due to managing and storing the data. Now, while data is expensive, and even a more challenging and important problem is that to extract that value from this data. So that's why actually you are going to store the data, because you hope to extract invaluable insights from this data. And there are several reasons for that. First, data is coming from, it's very diverse, heterogeneous. It comes from a variety of sources, from a variety of devices. The data is uncurated, there is no schema, inconsistent semantics, and syntax. So the integration of this data from all these sources is a huge challenge. And this is a very different word than you are used in for the last 40 years with a database. So we have curated data, schema, consistent semantics, and everything. Now, even after you collect this data, it's not the easy way to get a good answer, to get a high-quality answer and a timely answer. So really, the challenge here is to maximize the value from the data, from this data, by getting the best possible answers. We believe that in order to address this big data problem, we need to have a multifaceted approach. And fundamentally, to improve the data analysis, we can make improvement on 3 dimensions. One is to improve the scale, efficiency, and quality of the algorithms. The second is to scale up the data center so we can run the same algorithms faster and faster. And the third is to leverage the human activity and intelligence. And furthermore, we believe that in order to be successful, we needed to have an integrated approach in which we adaptively and flexibly combine all these 3 dimensions. So to give you a little bit of context, so here is that in this our 3D solution space, how some of today's application and services fit. So infrastructure software like Hadoop and database systems like Oracle are mostly on the machine axis. The review engines like Yelp and Amazon Mechanical Turk are mostly along the people axis. And analysis and statistical tools like MATLAB and R, implement sophisticated algorithms, but they do not scale very well. Now, what about these new other services like Google Search? Well, Google Search scales very well and implements sophisticated algorithms, and also they use the feedback from the users in order to improve their queries. And, you know, everyone saw, we saw the success of OAS on IBM during the past few days. This implements quite sophisticated algorithms scaled to several tens of machines, at least in the current implementation, and use also people to incrementally improve their knowledge base. Okay. However, in general, these solutions represent fixed points in the design space. So what we really need is techniques to dynamically pick the best operating point in this space to provide the best answers, given a budget of time and resources, and of course, given a data workload. So to tame this big data problem, we have created, and I'm happy to announce here, the AMP Lab, where AMP stands for Algorithms, Machine, and People. And the mission of the AMP Lab is to make sense of data at scale by tightly integrating algorithms, machine, and people. Okay? So in this lab, we are going to work to improve the solutions along all three dimensions: better algorithms, better infrastructure with higher scalability, and a better integration and leveraging of the intelligence and activity of people. Okay? And we are going to bring all of this together and unify them in a single system. And this is AmP Lab, how it looks on our 3D, in our 3D solution space. So currently, AmP Lab consists of 9 faculty members, 5 postdoctoral students, and between 20 and 30 students. AmP Lab has a broad expertise, including systems, networking, algorithms, statistical machine learning, databases, security, and mobile platforms and applications. Also, we are at a great start. We have a great list of sponsors here, and I would like, starting with Google and SAP, which are the founding sponsors of the lab. And in addition, we have another great list of sponsors, including, like Amazon, eBay, Huawei, IBM, Intel, Microsoft, NetApp, NEC, VMware, and Cloudera. So next, I'm going to talk in turn about each dimension in our 3D solution space. So I'm going to start with the algorithms. So today's algorithms, and in general, and in particular, the state-of-art machine learning algorithms do not scale well with respect to the data. So in many cases, when you have big data, it's prohibitive to process all these data points. So what does this mean? So let me take an example. So here we want to find a true answer, and we want to employ an algorithm, and we are going to feed the algorithms with data. And of course, as we give new data to the algorithm is expected to improve the answers and eventually to converge to the true answer. But now, the problem is that, say, we cannot process all the data. So you need to stop somewhere. So where do you need to, how do you know where to stop? So our answer to that is that we believe that giving any problem data and budget, we need algorithms which are going to provide error bars on every answer. If you have these error bars, now the question when to stop is relatively easy, right? So you are going to have some accuracy requirements, so it's a threshold on the error bar. So whenever the error is lower than that threshold, you are going to stop. Now, this plot represents the estimate versus the number of data points you feed in the algorithms. But this is not the most interesting relation. The most interesting relation is the estimate versus time. Because what you really care, giving a time budget, how fast you are going to get the answer. Right? So let me use the time now on the x-axis. And now let me pick 2 algorithms. One, sophisticated one, in which will take quite a bit to process the entire data, but you'll have pretty good error bars, which of course, as you get more data, they are going to go lower and lower. And the simple algorithms, which process the data much faster. So eventually, it's going to finish processing the data much faster than the sophisticated algorithms. But, it's going to get, at least when it operates on less data, worse error bars. So here you are going to have, there are kind of 3 regimes in general. One, the first regime, you have, the error is too high. So the data, the result is quite, is not very useful. In the second regime, you see the error bars of the sophisticated algorithms are lower than the ones of the simple algorithms, right? So in this case, you have a time budget which fits in this region, you are going to pick the sophisticated algorithm. And finally, once you process more and more data, because the simple algorithm is faster, it's going to get lower error bars than the sophisticated ones. So if your time budget falls in this region, you are going to use the simple algorithm. But what you really want is that given these problems and data and the time budget, you want to automatically pick the best algorithms on this machine learning algorithm spectrum. So that's the challenge. So the next dimension in our space is machines. So many have said in the past few years that the data center is a new computer. However, this transformation is still in infancy. Today, data centers are still partitioned in special proposed clusters, which runs different software stacks, like you have Hadoop clusters, MPI clusters, database clusters, and so forth in the same data center. In addition, the performance in these data centers are highly variable and sometimes unpredictable. It's hard to program, so to build new applications, you need to build almost the entire software stack. You need to provide resource management, you need to provide probably isolation, storage, and so forth. Finally, it's hard to debug. So when it comes to machines, our goal in the AmLab is to make data center a real computer. And we are going to do this by innovating at 3 layers. So first, we are going to build a data center OS. The data center OS is going to allow to share the resources, the entire data center, between multiple cluster computing applications. By doing so, we are going to increase dramatically the utilization of the data center and therefore reduce the cost. In addition, such an OS, like any OS, is going to provide new abstraction and services. This will make much easier to build new applications. Example of new abstractions or such abstraction and services are shared memory, communication abstractions between applications, and so forth. So again, this data center will support not only existing cluster computing applications like Hadoop, MPI, Hypertable, Cassandra, and Dryad, and so forth, but we are also going to develop new such frameworks to support a new generation of application. So for instance, Spark, it's a cluster computing framework. We support interactive and iterative data analysis, like machine learning algorithms. SCAD is a data storage framework which gives the user the ability to trade between the data consistency and the query response time. And Pickle, it's a system which provides predictive, which estimates the response time of a particular query and also can provide the user the hint so that it can modify the query so that the response time will fit in its time budget. Finally, at the last level, we are going to build tools and with our collaborators, applications such as advanced machine learning algorithms, interactive data mining, and collaborative visualization. So the last dimension in our solution space is people. And I mentioned at the beginning that one of the main challenges with the big data is that the data is messy. So it's uncurated, it's unstructured, inconsistent semantics and syntax. However, so humans are particularly good at dealing with messy data. We do that every day. And to prove this point, there are several successful services today doing exactly that. So the Amazon Mechanical Turk provides a marketplace for microjobs. Quora, it's a question and answer service. Many Eyes, it's a platform which allows users to upload their data, and then other user can see the data in a different ways, using different visualization tools and comment on the data. And Galaxy Zoo is a platform which allows people to collaborate to tackle big astronomical research challenges. Okay, so now when it comes to people, the tenet of the AmLab is to make people an integrated part of the system. And in doing that, we want to leverage both the human activity, not only the data they produce, but also leverage the human intelligence, and crowdsourcing. in a more popular term. And this means we can get the people help to curate and clean the data, and we can send to the people the answers for which machines have a difficult time to answer. And then we can ingest these answers back and to improve the knowledge base of the system and better answer the next questions. But the other important use of this platform is that really to test and improve the algorithms. If you think about it, it's a perfect platform. So you are going to hear in the next talk about natural language processing and video recognitions, image recognitions, and so forth. And these are the kind of algorithms you are going to see a lot of advances over the next year. And this will be a great testing framework, right, which people are starting to use, right? If you build this image recognition software and so forth, what better test than presenting your results and other people's results to other testers, and have them decide which one is better. But in achieving this goal, we face a big challenge, and the biggest challenge is arguably that the answers we get from people are many times inconsistent and sometimes inaccurate. And this happens in all dimensions. It varies with the type of questions, the time when we ask the questions. If you ask a question at noon in US time, you're going to get pretty different answers if you are asking the same question at midnight, when you are going probably getting an answer from people which are in Asia. And of course the cost, how much you are going to pay for the answers. Now, we are not going to build all these technologies in a void. We do have a set of real applications and a great group of collaborators. So one such application is Mobile Millennium Project. It's a project led by Alex Ban from Civil and Environment Engineering Department from UC Berkeley. And this collects the GPS data and SMS information from messages from the phone to predict, to monitor the traffic in real time and predict it. It's microsimulation of urban development. It's another project which is led by Paul Waddell from College of Environmental Design from UC Berkeley. It's a crowd-based opinion formation. It's another project, and the idea here is to build a platform for opinion formation which cluster people. It's a scalable framework, platform. And the way to achieve scalability is by clustering people based on their interests and their profiles. This is led by Ken Goldberg from Industrial Engineering and Operation Research Department, UC Berkeley. And the final project, it's with Taylor Sittler from UCSF. It's on personalized sequencing. So let me say a few words about this last project. So today we are witnessing a revolution in data sequencing. So the cost of sequencing is decreasing 2.5 times faster than the Moore law. So this means that new sequence data is generated at a much faster rate. There is a natural improvement in the CPU and storage capacities. Now, the goal of this project is to take this massive sequence data and combine it with epidemiology and clinical data and come out with personal clinical decisions. And for achieving this goal, we need a new generation of scalable machine learning algorithm, software infrastructures. These are all challenges we are planning to address in the context of the AMLab. So let me put things in perspective. I was talking about all these applications. So where do they fit in this 3D space? So this is how we believe they fit today. But we are planning to take them at the next level and really improve them along all dimensions, have better algorithms, better scale of the infrastructure, and bring people or even leverage even more people in improving the solution of these applications. So this means that really we want to take them and improve them on all these axes. And just to give you an example, just to give you two examples. In the urban microsimulation, so today the goal is to answer questions like, what is the congestion, how the congestion on this street is going to change if we are going to place a new store. But the other question you can ask her more in a real time is that what detour you are going to put in place in case of an accident. If you change the timing of, of the traffic lights along the San Pablo Avenue, for instance, how is the commuting time along that street at a particular hour is going to change? And for opinion spaces, you can think about taking it and integrating with question and answer services like Quora or Amazon Mechanical Turk to cluster people based on their expertise, based on their interest and profile, so therefore we are going to come up with better, more accurate answers. Okay, so taking a step back, and if you think, okay, if we do all this work, what we are going to get in 10 years from now? Well, almost certainly, we believe that we are going to create a new generation of big data scientists. We are going to end up with a real data center OS, which hopefully will make managing data centers and writing application for data centers as easy as it is today for a regular computer. The machine learning, we hope to become an engineering discipline, and the people will be deeply integrated in the big data analysis pipeline. Now, it's a stretch goal. If we are lucky, we hope that one of the big questions is that, again, like I discussed, because you don't know what questions you are going to ask in the future, you don't know what data to delete. We hope that we are going to get a much better insights and the system will know what to throw away. And at even a higher level, we hope that to generate new knowledge that an individual person cannot generate alone. So in summary, the big data is a problem which confronts both large organization and small organization. But besides being a problem, the big data is an enormous opportunity. And we do, in the AMP lab, we do hope to address this problem and get to a new level of getting results with the right quality at the right time. And then our approach in doing that is to holistically integrate algorithms, machine, and people in one system. As I hope that I convinced during the talk, there is a huge set of research issues across many domains which ways to be addressed, and we hope to address many of them. And finally, I like to again answer to thank to our sponsors which actually made this lab and the research possible.
First of all, I liked your presentation very much, and I thank you a lot. And I take the liberty to make a rather unconventional comment. You are talking about interaction between algorithms and machine, that is computers, with human beings, which is a difficult task because computers and humans are on different footing, all right? Now, the trend is to transform humans into computers. But this is terrifying. We should transform computers into humans. Thank you.
Yeah. No, I think that's a great comment. But basically, what also I'll take away, and actually we know is that computers and humans, they have different strengths, right? That's why we want to transform one in another, right? If they are the same, there is no transformation to take place. So really what you want to build in this system is to get more than the sum of them, right? To exploit the strengths of each of them, machines and humans, and hopefully arrive at a much better answers. Yeah,
Hi, the question is about the slide that you had on people section. You mentioned the answers are imprecise. Answers are not clear due to imprecise questions, and people can decipher or answer those better. But then on the same slide, you had a challenge which said the answers are not. Can you go to that slide, please?
Repeat, please.
I think it's basically
So it's kind of a catch-22. You have
Is that the question? How
Yes.
how can people help cleaning the data? Well, first of all, the people who are going to clean the data are going to be different from the people who generate the data, right? So that's one thing. The second one is that if it's really some important data you want to clean it up, right? Then you are going to have the opinion of multiple people, right? And then you know based on the statistical measure of their response and their accuracy, and also the histories with which they provide accurate answers, you can do a lot in cleaning this data. And
yeah, I think that's good. It's just that that fact wasn't clear on the slide.
okay.
I was not going to ask, but anyway. In the light of what happened yesterday with Watson, as we know, they started this project 4 years ago.
Yeah.
And then they have these amazing results. So we are starting this project AmpLab. What would you like to see as the application for the whole infrastructure we're trying to do 3 years from now?
Okay, so the question is that, you know, the Watson has all these great results and it's a great achievement. Where are you going to go beyond that, right? What?
4 years from now.
4 years from 4 years from now.
Where will we be in 4 years?
Yeah. So I think that if we there are two aspects. Okay. So the first aspect is that in terms of one application, one champion application, what will be that we are going to be proud about it? I think that, you know, many of those applications, we can fundamentally improve them. But just to give an example, the collaboration with the UCSF to provide the personalized clinical decisions based on the sequence DNA and based on the epidemiologic and clinical data. I think if we can achieve that, that will be a great result. In addition, what we are going to provide in infrastructure. We are going to provide new techniques, new technologies, and new infrastructure, which we hope will accelerate the pace of innovation in this space. So it will be much easier for companies, for new, to start and come up with great application, which will integrate all of these aspects, much better infrastructure than today, much better algorithms, and people as a fundamental part in the data analysis pipeline.
So, suppose people had more questions about AMP. How would they get them answered?
So yes, please come by our open house between 2 and 4 p.m.
All right, thank you.
Thank you. I guess one of the lessons is that big data is mostly not data. It's encoded in natural language, where most of human knowledge resides. So the next presentation is about using natural language processing for data in data algorithms and knowledge. So the presenter is Professor Dan Klein. He's an associate professor in our department. He's very well decorated. In addition to his research, of course, he's very well decorated as a teacher. Dan is the recipient of the 2010 Distinguished Teaching Award, which recognizes teaching that incites intellectual curiosity in students, engages thoroughly in the enterprise of learning, and has lifelong impact. That's pretty impressive. That's the highest honor, by the way, by the Berkeley campus on teaching, and our department has about 12 of those so far, the second best in the campus. In 2009, Dan won the Okawa Foundation Research Grant, and in 2009, he was also awarded the Jim and Donna Gray Award for Excellence in Undergraduate Teaching. So, Dan?
Okay, can people in the back hear me? Okay, great. So I'm going to talk today about data that's in natural language format, as a lot of this big data is. And I'm going to talk about the interplay between this data, the algorithms we use to process it, and the knowledge it contains. So I'm going to start off talking about language technologies with a story of two dogs from the far side. So the first dog is over here on the left. This is what we say to dogs. Okay, Ginger, I've had it. You stay out of the garbage. Understand, Ginger? Stay out of the garbage or else. This is the dog you'd like to, well, I guess you don't want this dog because it's in your garbage, but this is the kind of communication you'd like to have with your dog. And over here on the right, this is the dog you actually have. What they hear, blah, 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 Ginger, blah, 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 blah. Okay, so the dog on the right's basically grepping for its name. The dog on the left is the kind of natural language technologies we'd like to build. The goal here is deep understanding. This requires context. It requires analysis of linguistic structure. It requires operating at the level of meaning and understanding. The dog on the right, which is the dog we've got, is kind of the reality of shallow matching. So shallow matching is really driven by robustness. Statistics are very important, but statistics can also be applied on the left in kind of a deeper context. The dog on the right involves scale, and we've heard a lot about large data and scale. And really, this approach of relatively superficial processing at massive scale has had some amazing successes, but it's also got some fundamental limitations. And going forward, one of the key things is going to be marrying this kind of scale and robustness and statistical analysis with the kind of deep processing that's necessary to get really at understanding. So let me say something about these amazing successes I referred to. So a lot of you hopefully know about the success of Watson, which is a large-scale natural language processing system. So what can Watson do? Well, it's really quite amazing. It takes things like this. A camel is a horse designed by this. Alex Trebek says it better than I do. And it gives replies like this. It's a horse designed by committee. Okay, and you heard a little bit about error bars before. There's some error confidence estimates here, and despite these numbers in the long run, Watson basically crushed humanity. So the question is, how can a system like this do this kind of stuff? Well, you know, I chose an extreme example, but how do you know that, I mean, how does Watson know that a camel is a horse designed by committee? Well, if you type in to Google, camel is a horse or something like that, you get some answers. It's kind of all over the web. If you look up in Wiktionary, there's this entry, a camel is a horse designed by a committee. There's a discussion about it on the phrase finder. Basically, this answer is kind of everywhere. And so at levels of scale, you actually, in some ways, the scale is forgiving, because if the answer is in many, many places, you maybe only have to find one of them, or you can somehow aggregate your confidence across all of these. And that can let you answer a lot of kinds of question answering. Now, of course, I don't want to downplay all of the other things that are going on in Watson, some of which we know about and some of which we don't. But there is a kind of fundamental limitation to these factoid question answering systems. So factoid questions are things like, what is the capital of Wyoming? And again, in some ways, especially these kinds of simple factoids are easy. What is the capital of Wyoming? Well, you know, that's also all over the web. But if instead you wanted to know how many US states' capitals are also their largest cities, also a reasonable piece of trivia, and you type that into Google, it's not so helpful. So it's not that this is a hard question, right? In fact, it's straightforward kind of data processing. There's cities, there's capitals, there's largest cities, there's states, you know, and there's some kind of operation you would like to have performed over this that's well within the capacity of the computer. The problem is shallow kind of surface matching isn't going to answer these kinds of questions. What we need is we need to be able to actually understand this question at a deeper level so that we can do these kinds of computations on the basis of the knowledge we've got. Okay, so what's going on here? What's going on here is the data is text. So text data is a superficial thing. So in today's weather, I apologize for all of the wet ice examples, but here's one. An iceberg is a large piece of freshwater ice that is broken off from a snow-formed glacier or ice shelf and is floating in open water. So there's your glacier. And that's some data in text format. You can do things with that text like say, oh, it's got the keyword iceberg, there's something in here about glaciers, and you can do something very superficial with that. But the reality is language itself isn't just this text, right? It's all this information underneath. And so just as the iceberg has a whole lot of ice under the surface, if you actually want to be able to process this language in a deep way, you need to do things like analyze its syntactic constituents. You need to understand the semantics behind it, how these words ground into some kind of contextual or perceptual reality, and so on. And this is really what we need in order to get further. So let me go back to this issue of successes of large data and language. And I'll give you an example from machine translation. So this is kind of the standard way in which machine translation systems like our research system here, or something like Google Translate work. So here's a source sentence. In this case, it's in French. Maybe you read French, maybe you don't. But if you don't read French, then you might go into a translation system and get an automatic translation of this. How are those systems trained? Well, you get human translations, and you have these pairs of input and output that humans have translated. And sometimes the humans get it wrong, or they translate it in some weird way. And there's all kinds of problems here I'm not going to get into. But to a first approximation, you've got a ton of examples of inputs and outputs. And you think, well, that's good. If I get more data, my translations are just going to get better. And that's right. So if you train on 1 times a certain amount of data, this is the translation you get out. It's really, really bad. In particular, it's got lots of French words in it, so it doesn't really help you. But if you and the reason why you have French words still in here is because the system hasn't seen these words before, and it's kind of passing them through and just kind of hoping they're English, and it's wrong. So if you give it 10 times as much data, now it's seen all of these words, you get translations. So remember the human translation here, that would be an interim solution which would make it possible to work towards a binding charter in the long term. We know all of those words with this amount of data, but we get it would a solution transitional, which would have lead to term to a charter to value binding. I mean, there's some stuff in there, but this is pretty dire. If we multiply the amount of data by 10 again, you get this would be a transitional solution, which would lead to a charter legally binding. You can now understand it, but you don't enjoy it. And if you give it 10 times as much data, you get a good translation. That would be a transitional solution, which would eventually lead to a binding charter. Okay, you might wonder what all these brackets are. These brackets are the pieces, kind of the chunks of the example translations which are being recycled. And you can see that with more data, larger and larger chunks are being recycled, and that contributes to the improved quality. Okay, so data, data, data. That's all you need. Well, that's not the whole story. That's actually part of it. So part of the story is you need lots of data. The other part of the story is you need good algorithms processing that data, because the information you actually want is latent. So in this case, we have a source input and output, but we don't know what parts of that source input correspond to the output. And if we don't know that, then we don't know how to translate. So this is what it's like to be a machine translation system. You get some maybe English and some Chinese, and there's your data. You know Chinese now, right? So the problem here is now maybe it's time to translate egg drop, and well, you've seen it over and over again in your data. But the problem is you don't really know whether this is egg drop or this is egg drop. And the problem here is an alignment problem. You need to know which pieces of the input correspond to which pieces of the output, and that's not in your data. That's a latent variable, and that means that's something you have to learn. And that's where the kind of better algorithms and unsupervised learning come in. Okay, so what do you actually need to do in order to do a good job of machine translation? Well, you've got paired data like this. So here's some English and Chinese. This one's not a literal translation. And what you need to be able to do is you need to be able to analyze the structure of the input, analyze the structure of the output, figure out how they correspond. You want to do these things kind of in a way that leverages as much of your knowledge of the structure as possible. But you want this to be done in kind of a primarily unsupervised way that detects all of the patterns that are in the data that are kind of beneath the surface. Okay, this is something we work on a lot. We've actually got one of the best systems in the world for this, and it's a critical bit. It's not just data, it's about figuring out what's underneath the data. Okay, let me take a step back and talk about data versus knowledge, especially when you start talking about things like Watson. These things tend to get conflated. They're not the same thing. So people, back in the early days of AI, they used to worry about things, classic knowledge representation questions like, how will we ever get a machine to know that ice is frozen water? How will we ever get it to know that beige looks like that? Okay, imagine that looks like beige. How will we get it to know that chairs are solids? This classic question of you and I know that when you sit in a chair, you don't pass through it. Easy stuff. People tend not to write this stuff down, even on the web. So there are some there's some deep questions. So, and these problems have been there forever. We have answers for them in AI, but that answer has changed over time, and it's going to change in the future. So in the 1980s, the answer was write all this stuff down. That failed badly. In the 2000s, the answer was get by without it. That actually kind of worked. And so we built a lot of very spectacularly successful systems that basically skirted by not with understanding, but with the illusion of understanding. And now, if you take something like a question answering system that gives you the right answer, but kind of in a way that kind of looks at a bunch of documents and finds common word sequences and gives them back to you, and well, it's not the illusion of correctness. It's really correct. It's just the illusion of understanding. The process by which it got that answer wasn't kind of a deep process, and that means that it's correct, but has limitations. So the future is going to be in 2020. We're going to have this knowledge, but we're going to be learning it from data. So I'm going to try for the rest of this talk to give you some examples of what that might look like and what that does look like now. So here's another sentence. Again, I didn't know the weather was going to be like this. I apologize for these examples. Hurricane Emily, which is apparently outside right now, howled toward Mexico's Caribbean coasts on Sunday, packing a lot of winds and stuff. Okay, so this is a long sentence. I'm not going to read the whole thing. The point is, if you want to get much out of this sentence, there's a lot going on. In order to get much out of this, you need to break it into its bits. So here's a syntactic analysis. The details aren't important, and it's meant to be too small to read here. It's actually the correct analysis, and we can build systems which analyze not just kind of the string structure, but this kind of underlying syntactic structure at accuracies above 90%. They do it well faster than you can read this text, and that's kind of an analysis to a deeper level than the surface, but it's still not deep enough. Okay, so we've got the best systems in the world for this kind of syntactic parsing in many different languages. How do they work? Well, one of the main ways in which they work is we show them examples of correct analyses, but in those correct analyses, there are issues like, well, the correct analyses tell you that there are nouns and pronouns. But the reality of language is there's more going on. There are many kinds of nouns that mean many kinds of things. Even for pronouns, so you may have learned about nominative case and accusative case for subject and object pronouns in a grammar class. The system actually learns all of this stuff automatically from the data. So in particular, it discovered, unbeknownst to linguists, there's actually 3 cases in English. There's nominative case, accusative case, and uppercase. This turns out to be kind of important for kind of structural statistical reasons, but it also learns kind of some semantic facts about nouns, like it learns that dates are different things from names, and there are first names and last names, and first parts of places and second parts of places and middle initials, and all of these things. This is the kind of information that would take a long time to write down and what wasn't successful when people tried to write this down, but we can learn automatically using the right kinds of learning algorithms. Okay, so now it's still the case, even with these parsers that are the best ones we know how to build, they still mess up. And when they mess up, they don't mess up because they don't understand how language is structured. They mess up because they don't understand what the sentences mean. So here's an example. They considered running the ad during the Super Bowl. You probably all know what this means as soon as you read it. It's actually ambiguous. Your NLP system is very good in your head. You may not detect the ambiguity. The ambiguity is that one reading is the correct one, which is they considered something, and the thing they considered was running the ad during the Super Bowl. There's another reading where they considered running the ad, and they did that while the Super Bowl was happening. Maybe they were bored with the Super Bowl, I don't know. So this is another reading, and it's not an impossible reading, but it's wrong in context. And so the parser is very confused and, in fact, gets this particular one wrong. Now, you can go to shallow information sources and get a lot of these right. So you can see that, well, running during happens about 3,000 times on the web, and considering something during happens less, though not that much less. More specifically, you can look for occurrences of running it during, which is unambiguously the left, or considered it during, which is unambiguously the right. And you can see that the left analysis maybe is more common on the web. You can fix a lot of errors. This is using knowledge that is in some sense large scale from the web, but it's still very superficial, right? It's not knowledge under the model of syntax or anything like that. This here is knowledge that's kind of on the surface. So we need to be able to go deeper than this as we go forward. Okay? So here's an example of deeper understanding, and this is the question of reference. So here's a question answering system. I guess it should be like an answer questioning system if this is going to play Jeopardy, but you can do the translation in your head. So the question here is, who signed the Serve America Act? Well, here's some information from the LA Times. It says President Barack Obama received the Serve America Act after Congress's vote. He signed the bill last Thursday. The president said it would greatly increase service opportunities for the American people. So the answer's in there, but only kind of. So if you look, actually, the answer is he signed the bill last Thursday. And that's not quite right, because you need to, in order to answer this question with this piece of information, you need to know that the bill is the Serve America Act and that he is Barack Obama. So you need to make this linkage that he and Barack Obama are the same and that the bill and Serve America are the same and so on. And if you can do that, then you can answer the question correctly. Now, there are other ways to answer this question correctly. You could hope there's another document that says explicitly Barack Obama signed the Serve America Act on Thursday or something like that. And if you're lucky, you'll get that. And if you're not, you won't. All right. So we'd like to be able to do this kind of linkage of reference. And this looks like a kind of a structural linguistic problem, but it's actually a much deeper thing. This is the contrast between names and entities. So you have this string, Barack Obama, or this string, Serve America Act. Those are these names that occur, and we can do string matching on them and things like that. But underlying all of this, there's this entity, Barack Obama, and this document refers to that entity in various places. And there are these other entities that the document also operates on. And one of the things that's going to happen for deeper understanding is we need to move from operating at this text and string level, where kind of there are words and names, to this underlying entity level, where there are these actual entities in the world, and we're learning information about them from reading, and then are able to kind of manipulate that information or give answers or whatever it's going to be. All right, so here is some output from a co-reference system. This is actually from our co-reference system when you don't give it a lot of data, so it makes mistakes. It is nonetheless, even in this form, basically state-of-the-art as of, well, before our other system. But the input here is America Online announced on Monday that the company plans to update its instant messaging service. And you read this, and you know that America Online is the company, and it's, the pronoun refers to America Online, the company. And then there's this messaging service, which is neither of those things. The system actually messes this up. It gets some of it right. It knows that America Online's there. It knows that it's is the company. And it knows there's an instant messaging service. But it doesn't know that America Online is the company. It thinks there's some other company out here. Okay, so what went wrong here? Well, it's, the knowledge of language was fine. It understands how pronouns work and all of that. What really went wrong here is a knowledge failure. So the knowledge failure is that America Online is a company, but the system doesn't, and so it messes up. Well, how will a system ever know that America Online is a company? Well, it could look it up in Wikipedia. America Online is an American global internet services and media company. Okay, so the information's there, right? The knowledge is there, but the data that it's in is not actually trivial. If you want to get the information that America Online is a company from this source, you actually have to run co-reference on this, right? You need to know that America Online co-refers with the company, and so it's kind of a chicken and egg problem. So if you want to be able to get access to all of this information that lets you get access to more information, you've got a chicken and egg problem you have to solve. And that's actually something that we do have an approach for. That approach is unsupervised learning inside a model. The way that works is you've got your data, and okay, you've got lots of data maybe. You've got your data, and what you do with your data is you write down some probabilistic model. And in that model, there are random variables. Those random variables represent various things. Some of those random variables are the observed things, like all of the words in your document. Those are things you get to see. Other variables represent hidden things you'd like to learn, but which you don't see, and that might be things like the entities and the relations and the memberships of this is a company and so on. That's all the hidden structure. And importantly, what the model does is it connects the hidden stuff up to the observed stuff with statistical dependencies. So you describe this process by which the stuff you see can be explained by the stuff you don't see, and now you've got an inference problem. You've got a problem of what are the parameters that explain the observed stuff, and in the process of fitting those parameters, you discover the hidden stuff. So you then train this model, and once you've got those parameters, you can then take this model and inspect the hidden things. You can then also go to new data and use this knowledge that you've learned, and in the process, you basically learn to do co-reference by doing co-reference, and all of that knowledge is not taken in a superficial way, but a deep way within the model, and I think that's the future of these kinds of approaches. Okay. So how well does this work? Well, if you take our system, which is actually completely unsupervised, and you just give it the standard training data, it gets about 64 on this measure. It's kind of a weird measure, but higher is better. It gets 64. The state-of-the-art supervised system in 2008, which is essentially a combination of all previous systems, gets about 77. But if you take that same system that I just described and you give it all of Wikipedia and you give it all of Wiktionary and kind of all of the data we could get our hands on, then the accuracy jumps up to about 81, and this is now the best system in the world for this. Okay, so that was something about working, kind of linking up things within a document. If you're like me and you have a common name, so Dan Klein is a common name, and if you look me up on the web, you'll find my web page, but you'll also find another of me that's at George Mason University, and another of me that plays sports way better than I do. And then you'll find about thousands and thousands of others, and these are all different people, but then they co-occur, and it'd be really nice to have some representation of the underlying people that are actually in the world, and then to be able to say that not just inside a document document, but also cross documents these same people are referred to. It'd be nice to be doing, person disambiguation. It would also let us do things like multi-document understanding in a lot better way. So we talked a little bit about Watson. I'm going to say something very briefly about another news story that I'm sure you've been following very closely, which is this question of Lindsay Lohan maybe stealing stuff. There are like 10,000 articles on this, and they're all kind of slightly different, and it's possible you don't want to read them all. If you don't want to read them all, then maybe you want a summary, and so you have this problem, which is summarizing one document is hard, but now you've got thousands of documents. It actually turns out in some ways that's easier. You can kind of combine what occurs across documents at a concept. So basically what you want is you want to find sentences that cover the concepts in all of these documents, but yet somehow are compact, and we have a system for this. It's actually outperforms all previously published systems on this cross-document summarization task. And if you feed it all this Lindsay Lohan stuff, you get out this summary, which is much shorter than the documents, but has all the important bits, which is, she pleaded not guilty, and there's the charge, and then here's how much the necklace is worth, and then there's some commentary on the judge being upset, and then it ends with kind of a sentence that manages to lump together both what she's famous for in terms of movies and also kind of when the trial resumes. So here, I'm not going to read you this whole summary, but it's not bad. Okay, I want to take one more step further back, which means further forward, which is, I've been talking about understanding and deeper understanding, and so far that's been kind of strings and then syntactic structure and then reference structure and kind of going deeper level by level into this chain of understanding. But of course, when we use language, we use it in a very situated way. So I'm usually talking about something. That thing is often in the real world. And if you imagine, a mobile robotics application where you've got a robot running around your house, you're going to want to be able to tell it to do things like put the pillow on the beige love seat. And probably it's not going to then start grepping news stories to try to figure out what you mean. This is a case of needing to now kind of, as we get deep enough understanding of language, we need to start integrating with everything else that's going on around us in terms of vision and robotics and things like that. So how would you actually address this issue of understanding? Here's a simulated scene, so this is sidestepping some of the vision issues. How would you be able to process something like put the pillow on the, or even just understanding when I say the beige love seat that I mean this thing here? How will you know that? Well, this is something that could be, really hard if you try to do it in a superficial way. But if you actually have models of these objects and you have a compositional semantics, then you can do things like go and say, well, we know what beige is, right? We can actually get a lot of information from this large data context. So here's a bunch of beige stuff that actually, oh, it actually does kind of look beige. So here's a bunch of beige stuff. So we have some idea of which things might be beige. And then what about love seat? How are we ever going to know what that is? Well, it turns out that there are 3D modeling collections like the Google 3D Warehouse. Here are a bunch of love seats. And now you still have this hard vision problem of, this love seat isn't exactly the same as the one I've seen before. But if you know what each of these pieces mean, and you know what beige is, and you actually know what love seat is in a way that's grounded in some perceptual context, and you understand kind of what prepositional spatial semantics means and what it means to be on something, and you have a way of combining all of the bits of the sentence up piece by piece in a grounded way, now you can actually figure out what, you as a robot, what you're supposed to do with this, this pillow. Okay, so I'm going to end with kind of recapping some predictions. So today we have systems that are very good at finding information. I mean, I think search has been revolutionary. It's been an amazing success of AI and language, and it's vital. We wouldn't really be able to do a lot of what we do without it. Where I think we're going to move in the future is not just finding information, but synthesizing it. It's already to the point where you look for information, and it's just kind of duplicated everywhere. There's too much of it. You need to kind of synthesize it down. If we're lucky, then we'll actually be able to infer information from this. So what we'll be able to do is we'll be able to take all that information and be able to infer something that's implied by it. For example, how many US states' capitals are also their largest cities. That's not actually written down, but it's implied by what's written down. We want to be able to infer it. I also think that right now we operate at a level of keywords and names, and a lot of our processing is there. And over time, that's going to move towards an abstract level of entities. So we'll be able to actually talk about entities meaning something across documents and even also within a document. If we're lucky, we'll understand how to do this not just with people. Are kind of easy, right? I am actually a different person from those other Dan Kleins. But once you get to concepts and you get to talking about things that don't refer to people, this is all a lot murkier and gets into issues that are very hard. So another thing that we're going to see is this kind of move from knowledge-free systems that operate on the basis of surface patterns and structure to systems that acquire knowledge from text. And again, if we're lucky, it won't just be acquiring knowledge from text. It'll be relating that knowledge that's in text to knowledge that's coming in from cameras or rangefinders or mobile robotics applications or whatever it's going to be. Right now, to the extent that we talk to anything, we talk to the dog on the right, and we talk to search engines. We issue kind of small, short queries, and something comes back, and actually it's quite useful. What we'd like to be able to do is actually talk to devices in a more meaningful way, and in particular, we'd like to be able to talk to things like mobile robots, where what we're talking about is actually something that is in our world, and not just talking about something that's in the world of the search engine. And kind of to summarize the overall pattern here is that we need to be going deeper, not just kind of these superficial patterns, but also trying to get towards deeper understanding and moving these kinds of monologues where we say something, some kind of search result comes back and it's over, into some kind of dialogue where there's some shared context between the speaker and the agent. Okay, in conclusion, so far we've basically been trafficking as a community, as an industry, in these kind of simple algorithms that start to work well with large data. That's gotten us amazingly far. It got us way farther than kind of the deep algorithms on small data got us in the 80s. But really, to go further, we need to kind of marry this large data, robust scale, statistical learning with the kind of representations that let us operate at the right level. So that's algorithms that work with deeper structure. That's learning methods that take this data, the superficial stuff, and turn it into knowledge. And this needs to be with kind of systems that are contextualized, so systems that aren't just trafficking in strings, but also are kind of anchored and grounded in real-world meanings. That's all I've got. Thank you.
So you had an example of a Google search for how many states is their largest capital city, the biggest city. Interestingly, when I searched for it just now on my phone, it gave me the right answer right at the top. The answer's 18.
Yeah, it's also the case that if you searched for this about 6 months ago, it gave you my slides, which is why I use an older version of it. So you're definitely right that that some of these questions answer themselves. I mean, a classic one is how do you tie a bow tie? That's a classic Ask Jeeves example, and answers are curated. Questions that people have, they do get answered, they do get cached. So I'm not trying to say that this kind of large data doesn't solve any problems, and in fact, it solves a ton of problems. I'm just trying to say that it has limitations, and those limitations are structural.
Certainly your point stands, just a minute.
Okay. Thank you, it's a good point.
Hi, all the examples you gave and your predictions of what will happen in 2020, they strike me as passive, where somebody asks for information and an answer comes back. Is there any research into an algorithm making more active creation, such as something creative, like a short story, or we've all heard abysmal computer poetry, but is there anything which is actually worth publishing?
So let's see. So the question of there's two questions in there. Are we going to have active systems? I mean, I think that's definitely going to happen, but the active versus passive mode of interaction is more about the system design and what you want the system to do, rather than any kind of question of how the language works. The language works the same either way. It's contextualized the same either way, whether it's your initiative, the computer's initiative, or some kind of mixed initiative thing. It's a great question. The specific question of our computers going to be writing stories, in the 80s, you could write stories that were bad in one way, and now we can kind of write stories that are bad in different ways. I don't actually know how much demand there is for computer fiction, but there's a lot of demand for automatic generation of things like weather reports that are more mechanical, and I do think you're going to see a lot more summarization, a lot more generation, and kind of in general, this question of generation versus analysis. Historically, it's been easier to build a system that does generation okay than analysis okay, and that's because when you analyze it, you actually have to deal with human-created text, and you have to get it right. Whereas when you generate, there are many possible correct things, and you only have to find one. You don't need to be able to own that whole space.
Yeah, just a quick question about, so like a lot of the kind of, I guess, sentence diagramming and construction and connection of ideas stuff actually is very reminiscent of things that we saw in sort of elementary school and high school when we were taught, reading comprehension. And I was just wondering if you think that the techniques that you guys come up with for teaching computers to understand and read stuff might actually have some relevance to teaching people how to read and understand things as well.
It's a great question, and the question of kind of how any of this relates to education, it's a tricky one. So, for example, for machine translation, it's definitely done very differently than how we think it's effective to teach humans. A lot of that difference in the past has been because humans operate with language in a very grounded, contextualized way, whereas for machines it's all very structural and knowledge-free. It's a great question, and people do work on kind of tutoring systems, and there have been some advances there, but there's no simple answer.
And then if they had more questions?
If you have more questions, you're welcome to contact me. You're also welcome. There is a Center for Intelligent Systems open house, I think 2 to 4, on the 7th floor of Sutar Jadai. I think I got the details right. All right. That's the right answer. That's the right answer. Yeah, don't contact me.
All right, so moving right along to the next subject, I guess the story here is that Q&A systems are good, but using a system to make you more intelligent in real time in a transparent way is perhaps even better. So Avideh Zakhor, who's a professor in our department with an illustrious academic career, but even more so, an illustrious industrial career. She has been the founder and CEO of I'm sorry, I'm reading somebody else's illustrious career. She has been the founder and CTO of True Video, co-founder and consultant at UrbanScan, Inc., a co-founder and CTO of SignalMask, and optical proximity correction technology. She's also an IEEE Fellow and the recipient of the Okao Foundation Research Grant. Avideh?
Thank you, Kostas. To begin with, I'd like to acknowledge some of the staff members, graduate students and undergraduates, and also the people at Earthmine, Inc. who provided some of the data for the talk that I'll be giving today. So roughly speaking, the outline of my talk is as follows. I'll begin by talking about what augmented reality is, why is it important to work on it now, what are some current examples and applications, and in a more detailed way, I'll talk about image-based localizations for augmented reality applications and describe some of the work we're doing at Berkeley, and end by some future directions of research. So, just to bring everybody to the same page, what is augmented reality? It's enhancing or augmenting real or actual world to create a more satisfying user experience and perception. So it's really the joining of the virtual and actual reality. This diagram here has been credited to Milgram. On the far left, you have real environments, and on the far right, you have virtual environments. And somewhere in the middle, you have augmented reality. Dan Sanchez Crespo, who's at Novorama, once said that the real world is way too boring for many people. By making it the world a playground for virtual world, we can make it much more interesting. So here's some interesting possibilities for augmented reality. It's not here today, but suppose you're walking on the picture on the right, you're walking in an alley in a tourist area in an unknown country, and you come across people you don't know. It would be nice if there was a face recognition system that would recognize the guy on the left as a registered sex offender. I personally wouldn't be walking in that alley anymore. Or suppose you like this T-shirt on this guy's, on this person's who's wearing this, and you want to know, where would I buy that from? Or suppose you're driving on the left picture, you're driving, and as you're on your viewfinder, you can find out information about the shops you're passing by, the street you're in, etc. So these applications are just hypothetical, but the ones I'm going to talk about now in this slide are actually happen. So the top picture here is a heads-up display for a pilot. Actual information is displayed on top. Virtual information is displayed on top of the visor, indicating to the pilot some key things about the pitch angle of the airplane, the roll, the altitude, and other things. And since Super Bowl was just a couple of weeks ago, that's a perfect example. These yellow and blue lines that you see, they're virtually superimposed on the field. And to do that, you have to analyze the images and the videos and do that in a precise way so that the lines register with each other is quite a difficult task. But it's an existing application. There are a number of AR applications today. On the upper left, you have WordLens, which takes pictures of some text in a different language. It translates it pretty much the same way as Dan just talked about. On the upper right, you have a dish pointer for satellite. You can use it to locate where the satellite exactly is. Yelp, on the lower left, you have an example of a Yelp that superimposes on top of a cell phone information about what you're viewing. And on the lower right, you have Lyre, which is a new startup that provides generalized AR platforms. Most of these applications use GPS and orientation sensors. However, an example of an application that goes beyond that and perhaps uses camera and visual information to do such things is Google Goggles. Many of you might have heard of that. Here's a snapshot of it. It has several categories: landmarks, books, contact information, wine, logo, etc. While these are interesting categories, they're somewhat limited. It's okay if you can point your cell phone and the phone tells you that this is Golden Gate Bridge, for example. But if you're walking around any random street in San Francisco, it doesn't provide you information about all the other things that goes on in typical streets. So it's fair to say that most of the existing AR applications today leave a lot to be desired. There's a lot more that with today's technology and with today's algorithms we can do that currently has not made it to the marketplace. So why now? Why is it a good time to be concentrating on AR today? The first and foremost factor is the prevalence of mobile and handheld devices. There's lots of smartphones with lots of sensors on them. In fact, there's more cameras that are being sold on cell phones, packaged with cell phones, than individual cameras every year. There's coarse orientation measurement sensors. The fact that you turn your iPhone from landscape to portrait and it adapts the content automatically is just telling you it has an orientation sensor, even though it's a very coarse one. There's also coarse GPS on many phones, not differential, but just up to 10, 20 meters accuracy. And there's also coarse accelerometers on these devices that allow people to play games. So whereas in 1995, you had to have an attire like this, with a backpack and things hanging over your head and belt around your body and all those sensors hanging over you in order to do augmented reality, all you need today is just your cell phone. And there's plenty of good cell phones with lots of good sensors. Continuing as to why this is a good thing to do now, CPU cycles are incredibly abundant and cheap. Cloud computing has made that possible. Wireless networks are getting faster and faster. We're out of the CDPD days with 5 kilobits per second, and today we have 4G, which allegedly can do 700 or megabits per second for you. And most importantly, recognition, especially image recognition performance, has improved by leaps and bounds in the last 10 years or so. Pattern recognition has been an outstanding problem for 50 years or so, and quite a bit of progress has been made since the last 10 years or so. Just to give you an example, this red dot here, on the horizontal axis, you have the number of training examples to recognize 101 object categories in what's called the Caltech 101 database. And on the vertical axis, you have recognition performance. So in 2004, when this database got started, the performance recognition was around 16% or so. And by 2007, you can see the recognition performance has reached close to 65%. So there's been a lot of improvement in the image recognition world. So what are some underlying technologies for AR? To begin with, you need to have a suite of sensors to sense and recognize the world or the environment that surrounds a user. And more importantly, to localize the user. Where is the user? What direction is it looking at? What is it looking at? And for that, we have cell phones with cameras and GPSs and orientation sensors. Then you need to have algorithms to process this sensor data, signal processing, image processing, computer vision recognition algorithms, etc. Then you need to have databases somewhere in the cloud in order to look up the metadata or the enhancement or augmentation data that you want to be sending over to the user to create the augmentation process. And finally, to do that, to send it over, you need to have networks that are reliable. And so if you have intermittent connectivity, you might have to play clever games like caching some of the data ahead of time to give the illusion of connectivity, even though you've actually lost connectivity at some points. And finally, you need to present the data to the user, and that requires advanced work on user interfaces, rendering, and visualization. So as you can see, to get augmented reality to work, there needs to be a lot of advances in lots of different fields of electrical engineering and computer science, not just one, but all the way from sensing technology to algorithms to networks, databases, and user interface. And for the rest of my talk, I'm going to talk about the first part, the suite of sensors to localize the user. So why is that an important problem? Well, to begin with, a couple of days ago, Eric Schmidt at Google at the Mobile World Congress in Barcelona, Spain, said that location and mobile ads would revolutionize commerce. It's a billion-dollar business right in front of us. So not so much unlike location in real estate, but here we need location for AR, right? So what do I mean by localization? And I mean specifying and figuring out exactly where the user is, and that's X, Y, Z, and its orientation. Which direction is it using? That's three angles, three orientation angles, yaw, pitch, and roll. And we need to do that for both indoor environments and outdoors. So let me begin with the simple case of, well, if we're outdoors, we can quickly find out where we are if we use GPS. Well, first of all, GPS doesn't provide orientation. Also, it's not accurate for most augmented reality applications. Even if you were to use differential GPS, which is something military uses, it only gives you centimeter accuracy. It doesn't give you pixel level accuracy in order to superimpose the metadata to pixel level accuracy on top of your camera images. Also, if the satellites are not visible to the mobile, then you don't have a GPS reading. I had a student in my class who said he tries to track his wife who works in the financial district, and many times the application that he runs tells him that his wife is in China or Bangkok or something. And in particular, if you have urban environments with tall buildings like the San Francisco Financial District or Manhattan, many times these are exactly the places you would like to run these kinds of applications. You can't because of the invisibility of the satellite. So another possibility is to use what's called cell tower triangulation. So and this uses the locations of the base stations or the cell towers that the carriers, wireless operators, has to triangulate in order to localize the user, as shown in this picture. In fact, FCC has a mandate for 9/11 emergency services and also law enforcement applications where it requires cell phone manufacturers to satisfy these requirements. 67% of their phones must be localizable within 50 meters and 95% within 150 meters. So even if you have no GPS or GPS is out, the cell phone triangulation, to some extent, to within 50 or 150 meters, tells you roughly where you are. And finally, another way to localize is using Wi-Fi, but as you all know, that has a lot of privacy implications. So to summarize all these things, there are existing ways to localize, but none of them provide orientation, and none of them are pixel accurate. So the most obvious thing to do is to say, if you want to have pixel level accuracy for your localization, you better use the cameras on your cell phone to achieve that pixel level accuracy. And the way you do that is you come up with, if you use the image databases that already exist, take a picture, match your picture to the image database, and in that process, try to figure out exactly where you are. And so in what I just described, you might be asking, well, where are these image databases? Well, thankfully, over the last 10 years or so, a large number of image databases have been commercially available. The most notable ones are Street View from Google, Bing Maps from Microsoft, and the particular company we collaborate with is Earthmine in Berkeley. So here's examples of Google Truck with all the laser scanners and cameras on top on the upper left, and the lower right is the Earthmine truck with similar sensors driving around streets. I'm sure you've run into some of those. And so on the right, you see a picture of a street view of Corey Hall at the intersection of Hearst and La Loma. And on the lower right, you see an example of a Google Earth 3D model of New York City. So these image databases are not only just images, but they're actually, by now, they're having some actual 3D data information, which, as you'll see through the rest of my talk, can be very useful in AR applications. I like to shamelessly put a plug here for the work we did at UC Berkeley. The 3D Google Earth was actually licensed from some of the work that was done in Berkeley between 2000 and 2006, where we put laser scanners on top of cars, and we flew helicopters to collect aerial lasers and aerial pictures, and build point clouds at the ground level, and point clouds and texture images from the top, and merge the aerial and the ground-based data to come up with complete photorealistic 3D models that are both, you can do virtual walkthroughs through them and virtual fly-throughs. And for example, if this was the satellite picture of Berkeley in 2006, it was just a picture, and after you put the 3D models that we generated, it would give you something like this. So you can imagine that if you have access to such 3D databases, you can do a lot more with AR applications than without the 3D information. Anyway, coming back to the image-based localization, how do you use image databases to localize? And the answer is pretty simple. You start with you take a query image, you detect features in it, and the most popular features these days people use is what's called SIFT features. And then you also go to your image databases and collect all the SIFT features in all the images, and you build some sort of a vocabulary tree or a KD tree. And you can think of it as a coarse vector quantizations. You're coarsely quantizing the features. And then when the query image comes, one feature at a time, you feed the features into this tree, and each time you feed the feature into a tree, each of the image databases, some of them get a score, get a +1 score added to their overall score if they share that feature. And by the time we've fed all the features of the query image into this box, all the image databases have a score accumulated, and the one with the largest score is the good match. So this technique has been around for about the last 5 or 6 years. And in fact, Rick Zaleski and his colleagues at Microsoft in 2007 published a paper that does city-scale location recognition. But the problem with this scheme is that the performance degrades with the size of the images in the database. So for example, if you have 2,500 images, you can have a recognition rate of 65%, but by the time you get to 30,000, it drops down to 45% or even lower. So this approach really doesn't scale very well. So what we did at Berkeley is we took this divide and conquer type approach in order to come up with a scalable solution to this problem. And we started by dividing a large geographic area, let's say the Bay Area, for example, into overlapping circular cells. These are these circles that you see here. They're centered at vertices of a hexagonal lattice. And really what inspired us was the same way as that the operators use these cells to hand off your call from one cell to the other. We were kind of inspired by that in coming up with this geometry. So each cell will then have a set of image databases in it, and each cell has its own KD trees, which is used for doing recognition or localization. And at the same time, we're assuming we have some coarse location reported by the cell phone to approximately tell us which cell we've fallen into. In fact, we come up with this notion of ambiguity circle, which is the centered around the reported location by your cell phone. This is the area of ambiguity reported by your cell phone as to roughly where you are. So in this case, this orange circle here is showing you the ambiguity about your location. The center is probably the most likely, but you could be anywhere in that disk. Okay? But if you're using, for example, the FCC probability distribution curve, it might not be a circular disk. It could be high at the center point and then die off exponentially as you go to the sides of it. It almost doesn't matter. So the question that comes up is, what's the optimal geometry for these cells? How should these cells be overlapped? So if you call the radius of each cell to be R, and the ambiguity circle for your location to have radius G, and the distance between the center of the cells, D, which is really what controls the amount of overlap you have between your cells, then it would be kind of nice if for a given size of ambiguity circle, that entire ambiguity circle, location ambiguity circle, would entirely fall into one cell. Because then if you have that, then you can just look up your answer in one KD tree, and get the location information. It turns out after you do some geometry, if this condition is satisfied between D, R, and G, then you can get away with just one cell search. So here's a picture of these cells superimposed on top of downtown Berkeley. And as you can see, there's these petal areas and there's non-petal areas. And if you assume that D is equal to R, then each image is going to fall into 4 cells if it is in the petal area, and it's going to fall into 3 cells if it is not in the petal area. What does that mean? It means that if you have 0 ambiguity, you can search in 3 or 4 cells and combine the results of these 3 or 4 cells in order to improve the accuracy of your recognition and localization. This is not so different from error correction codes in communication, where you build some sort of a redundancy into your system to improve performance. And you'll see that in a few minutes that it actually works. Now, if you have ambiguity with regards to your location, you don't exactly know where you are, which is typically happens, then your ambiguity circle, you can show it can overlap between 3 to 9 cells, for example. In that case, you search in all the possible cells that your ambiguity circle overlaps with, even though only 3 or 4 of them have actual images that you're looking for. But again, by doing so, you're improving the robustness of your localization. So to summarize, here's a flow diagram of a system. You start with your query image with some sort of an approximate location. It could come from GPS, it could come from cell tower triangulation, whatever. You find the SIFT features, you find the intersection of the ambiguity circle associated with your location with all the cells. This tells you how many cells you do the search, and then you do these parallel searches in a number of cells and then combine the results together in order to get a good answer. And to illustrate some of these points pictorially, here's an example of, again, Berkeley with all the cells and the center point. And here we're assuming that there's no location ambiguity, and this is the cell that this location falls into. And this is the single cell, sorry, that it falls into. And these are the 4 cells that it falls into also. Now, if you have some sort of ambiguity around it, which is the yellow circle, then it can, these are all the 9 cells that you have to be searching in order to get your answer. So to improve these results, we do a number of what's called filtering, post-processing type things. So for example, we can do geometric verification by looking at the features in the query image and the database image in order to make sure that we get rid of the bad features and to improve the voting process. You can also do what's called key point matching to achieve that. Yet another way to do things is to use machine learning techniques in order to learn from a data set as to the probability distribution functions and use those with your feature sets in order to improve the results. I won't go into the details of it, but I would only say one thing, which you've already seen twice in the first 2 talks, and that is by going through this machine learning process, we can also come up with the confidence levels for the answers that we get. So we not only come up with the ranked order list of best performances, but also we can come up with confidence on what we have on each of the ranked order returns. And this is shown here. And so this confidence matches pretty well with the correctness of the answer that we get. And so the system can not only tell you what the best retrieved image is, but it can also, if the confidence in the best retrieved image is not high enough, it can give some sort of a feedback to the user in order to recapture another image in order to localize better. So just in the remaining time, let me just quickly tell you about the EarthMine, the experimental results that we have. We use the EarthMine data sets. Each one of these green circles here are panorama locations that we took. In each location, there was a panoramic image captured. We sampled that panorama along 12 angles, and we get these things. We throw away the top 3 and the bottom 3 because those are just down the street and they're not looking at facades of buildings, which is really what we need to localize. So our image database has 2,000 of these panoramas. This results in 25 cells. Each cell has 1,500 images and a total of 12,000 geotagged images. This is over about 1 square kilometer of Berkeley. And we have 3 query sets. Sets 1, 2, and 3 were collected with a camera. And set 4 was collected with a cell phone, actual cell phone. And we also, for experimental purposes, we used geotagged images on the GPS of the cell phone, but because that was only accurate to 10 meters and we needed to simulate to 100 meters, we played a lot of extra games to make that happen. So here's the performance of what we got. On the horizontal axis is the number of top matches, 1, 2, 5, and 10. So the bottom curve is when you use just a single, and the vertical axis is the percentage match that we get. So if you just use a single cell, you get 65% accuracy. If you combine the cells, it jumps up to 75%. And then if you use geometric verification, you get the green curve, which is at 85%. And finally, if you add the machine learning, you get all the way to 87% for the top one answer that you get. And these results are all for query 3. Which was done with variable focal lengths. But if you apply the same algorithms to query 1 data set, which had the fixed focal length, you get performance all the way to 90% or so. And finally, if you use your cell phone data, we've done just limited experimentation with the cell phone, you can get 80%. This is without adding the machine learning and various other things. So the performances are quite nice. And just to compare, there was a different group at Stanford and Nokia that used the same Earthmind database. And if they used the same images that they trained with the testing, they would get 85% accuracy. But if they just used cell phone images like we did, the performance is 32% as compared to 80% that we get. So there's leaps and bounds of improvement by doing so. And once you're done with identifying the images, then you can, if you've tagged your database, you can transfer those tags in a nice way to your query images. So we use the Earthmind tagger to that tag, and then it transfer it to 3D, and this is where the 3D really comes in. Transfer the 3D tags onto the panoramic images, and then finally transfer that into our query images. So here's a tag for a particular store in the database that has been transferred into the query image. And we've found that 90% of this tag transfer works flawlessly. And here's an example of tags being transferred onto cell phone imagery. So future technical challenges, really the main one is the optimum division of work between the client and the server. There's computation issues involved, communication issues, and delay considerations. If you want to do one-shot localization, maybe the work can get done on the server. If you want to do it real time and track the user as the user moves, you probably have to do some of it on the handset. You can also play games by having the users populate the database by transferring the pictures to the database so that the places that are more popular will have more images and you have better likelihood of localizing yourself than places that don't have as many images. And finally, in the last minute or so, let me talk about indoor applications. Why do AR in indoors? Well, it's a holy grail of mobile advertising and location-based services, but the problem with indoors is there's no GPS, so you can't really even coarsely localize where you are. And that's not only problematic for your AR applications, but also problematic for making 3D models of indoor environments. So I'm happy to say that over the last 4 years, we have a program at Berkeley in our group where we have developed the first 3D indoor modeling system using a human-operated backpack system. It's equipped with laser scanners and cameras. And it results in 3D models that you can interact with virtually. That's shown here. This is the 4th floor of Corey Hall and the 3rd and 4th floor. And the reason we have a backpack is because we want to be able to do difficult environments like staircases that robots and wheeled devices cannot do. So it turns out that an important problem in creating these 3D models is loop closure. Loop closure means detecting where you've come up to the same location. And what happens is that we use camera images in order to automatically detect where the backpack has come to the same location. And why am I talking about that? Well, it turns out that that same image-based loop closure detection technique can be used for indoor environments for AR localization. And we've actually not experimented with it, but the fact that our loop closure techniques work flawlessly, like shown here, is kind of an example to it. So the details are, I won't go into the details of it, but again, some sort of a Bayesian framework, fab map, post-processing, etc. But the upshot is the very same techniques that we develop for outdoors, we can now develop for indoors. So just to wrap up, almost certainly many more AR applications will appear on your cell phone, and really the driving forces will be mobile advertising and location-based services. And most likely and most compelling applications would be 3D AR applications. So the fact that now you have a cheap Connect device that can do 3D recognitions and can provide a 3D user interface will allow us to interact in the world, not just using a viewfinder on your camera, but with the actual 3D device. And I think this is really where most of the excitement in the future will be. And the goal is to blur the line between the real and virtual. So AR is no longer the technology of the future. All the key ingredients are here, and it's a matter of putting these together the right way to create the right user experience. And I'll stop right here.
Rely on less precise localization techniques?
The question is, do you really, why, you understand why pixel level is important for some, but if you didn't have it, are there apps that can take advantage of less accurate?
Right. I guess you could, but for example, for gaming applications, I would say if you're interacting with objects in a room, it's pretty, and you're trying to grab an object in a virtual way or shoot a person or whatever, you need to have some sort of an accuracy. So if you relax that when you're writing the application, yes, you can get away with it. And you should, as an application developer, you should probably take that into account. I think the closest from an industry point of view you come to that is Lyre system, where it provides a kind of a platform for people to write it. So if you incorporate that in the platform, that would be a very useful thing.
Okay, one more. Next.
Thank you very much. I was fascinated by your brilliant presentation. Thank you. You essentially talked first about outdoor localization, let me say, and then said something about indoor. This indoor is now pretty advanced because using results in homeland security localization of terrorist actions inside the city. But now I would like to make, and please forgive me again, an unconventional comment. You essentially presented very brilliantly ways to improve our senses, to make we able to look at far distances, to take decisions, and so forth. However, all those devices, the more better, the more true is what I say, are no more quote-unquote instruments, but are becoming prostheses. And if they are becoming prostheses, now a person without a cellular is not a human being, he's a monster, he's a savage, all right? So they're becoming prostheses. And so the close range in time solution is improvements as the one you presented. But the far away in time solutions are in the hands of bioengineering. They should be included in human beings. I'm not in a position to say how, but bioengineers, if anybody here, will applause me, okay? Thank you.
Thank you. And we have, in terms of bioengineers, I guess one comment I would make is that we have activity at Berkeley, Jose Carmena, who can do brain-machine interface and read your mind. So maybe Jose can design contact lenses or visors that we can put in our eyes and be able to virtually look at what goes on. So you're right. That falls into the user interface aspect that I talked about, and it's not to be taken lightly because user interface as a field has a tendency to have been ignored quite a bit, and the progress is extremely slow, has been very slow. But it is crucial to this technology to interact with it in a natural way that's easy for us.
So reading your mind and putting it on the web, that's an interesting thought. But we're not going to go that far yet. We'll talk about the sensor swarm. The idea here is that big data is useful in many ways, but more and more it does not come from people, it comes from things. And this is going to be the theme of the next presentation. I would like to acknowledge two people involved in this presentation. One of them is not here, Jan Rabaey, Professor Jan Rabaey, known to most. Jan is one of the visionaries behind this idea. And he's the recipient of the Semiconductor Industry Association 2010 University Researcher Award, the 2009 European Design Automation Association Lifetime Achievement Award, and he's a pretty young guy, by the way, and the 2008 IEEE Circuits and Systems Mark van Valkenburg Award. The presentation is going to be given by one of the close collaborators. He's Christopher Pister, Professor of Electrical Engineering and Computer Sciences at the University of California at Berkeley, founder and CEO of Dust Inc., and founder and CTO of Dust Networks. Kris was awarded the 2009 International Society of Automation Albert F. Sperry Founder Award. And I would like to read you the citation of that because it's kind of interesting. This is ISA's Outstanding Achievement Award and recognizes an outstanding technical, educational, or philosophical, I'm not making this up, philosophical contribution to the science and technology of instrumentation systems and automation. So, Kris?
Thank you, Kostas. So unfortunately, Jan is in New Zealand, so he can't give the talk. So I will try to speak with a Belgian accent for the rest of the presentation. So Jan likes to start this one by looking back in order to look forward. So back in 1990, the InfoPad project was getting going, and the idea was, we'd sort of gone from one person sitting in front of one computer to everybody having a computer or terminal on their desk to then everybody having a computer, and InfoPad was sort of pushing that back in the other direction. No, you're going to have a connected device and be interacting with bigger computers elsewhere. So to many, this is the birth of the wireless tablet, and kind of led to the future that we live in today. And a little after that project, I got started on a project of my own to see what would happen if you could make really little tiny wireless sensors that you could put everywhere. And despite on a day-to-day basis, what seems to be an incredibly slow pace of progress on that project overall, I was driving into work the other day and thinking that actually there are some signs that we've had some successes. That I was driving in my ancient hydrocarbon-fueled car and thinking about the fact that all the sources of hydrocarbons now are actually being monitored with wireless sensor networks in production. And the transport of those hydrocarbons is in vessels that are being monitored with wireless sensor networks in production. And the refining of those hydrocarbons is actually being done in refineries up here. This is a picture of the Richmond one, where actually they've got a wireless sensor network that covers that entire 5 square kilometer refinery with wireless sensor networks. And then there's a rail yard in the upper right corner of that place that transports the products of that refining, and those tank cars and the contents of those cars is being monitored with wireless sensor networks, and the rail cars themselves are actually being monitored with wireless sensor networks. And then that gas goes to fuel my car, and I drive around in a city where actually, if you're in San Francisco, not only are the parking spaces being monitored with wireless sensor networks, but the stoplights, street lights are being monitored with wireless sensor networks. And the place where we buy the gas, the energy consumption of the refrigerators and so on is being monitored and optimized with wireless sensor networks. The buildings that we go to are constructed with steel that is created in plants where they're improving their efficiency with wireless sensor networks. And in fact, the buildings themselves, the HVA systems and the computers in those buildings are being cooled by systems that are being monitored by wireless sensor networks. So it seems like the progress is really, really slow, but I guess there actually has been, something has happened in the last 14 years. So I'm encouraged by that. But all of those things have really been wire replacement applications. I mean, there's a couple of them where it would have been really inconvenient to run wires, but you probably could have done it. So it's all about cost. And now, now in 2010, we have to kind of look forward, what's the next 20 years going to look like? And I really enjoyed the 3 earlier talks because I feel like they're all talking about the things that are going to be enabled by this next generation of the mixture of sensing and actuation and computation in this sort of future wireless-enabled world. So, where are we going to end up? And it's pretty clear that we're getting down to molecular size devices, and that the devices that we have are not just going to end up on chips, but they're going to end up on clothing, they're going to end up on the wallpaper and so on in circuits that are measured in square meters, not in square mils. And wireless connectivity, I don't know if it's going to be every object, but certainly any object of any kind of value is going to have its own wireless connectivity on it. And this idea, Jan likes to talk about 1,000 wireless sensors per person on the planet, so 7 trillion, and I think that is, we're on our way toward that. And it really, the functionality is all about the interaction of the sensing, computation, communication, actuation, and power and storage, and how you trade off all those things is what's going to make this work. So, Jan calls this the swarm. We know about the cloud, and then I think he calls this the fog around the outside, and then ultimately the swarm at the edge, where for every one of the billion or so cell phones or tablet devices or what have you sold each year, there's going to be 1,000 devices out there that they're communicating with and interacting with on a regular basis. And this leads to kind of a different version of Moore's law, maybe related to Metcalfe's law also, that it's all about the connectivity. It's all about the fact that all these devices are out there and they're interacting with each other continuously and interacting with the machines that are interacting with you. And so if you're doing the natural language processing or the image understanding or localization with images and virtual augmented reality, all of that is going on in the background because of this connectivity. And it's all regulated by or sort of strongly dependent on how much energy you have available at any part inside that swarm, which makes it really, really challenging. So Jan likes to read science fiction. I do as well. This is one of my favorite books as well as his, A Deepness in the Sky, where in 1999, Werner Vinge has his character Pham Trinh Le talk about these tiny devices that are communicating wirelessly with each other and able to localize and able to sense and even do a little bit of actuation and scavenge energy from microwaves in the environment. And ultimately, they not only save the planet, they save 2 entire civilizations. So I like the smart dust saves civilizations angle on this. So this is Jan's motivation. Many of you may know Werner. He's a professor of computer science and a friend of mine. And so he actually got some of those ideas from looking at the Smart Dust project. So Werner is saying we're gonna save civilization with wireless sensor networks and computation. And in the near term, we've got some more practical things to work on: energy, transportation, agriculture, environment, home automation, disaster response. These are all the things that you'll see people in Citrus working on today, and are absolutely a part of that future. But then, sort of to address your ideas there, I think bio-cyber is Jan's term for where we're headed with that, the things that Jose Carmena is doing with brain-machine interfaces, the kinds of implants and things that a variety of people are working on at Berkeley, is another way to make that interaction with the computer be as seamless and natural as possible, or in some cases, prosthetically replace a capability that is no longer there. So Jan likes to say that we're headed not for the InfoPad, or take 3 words away and you get or 3 letters away and you get iPad, but actually to the unpad. That in fact all those devices disappear, and it's all just our natural interactions with the environment. So the Wii is really still just a pad of some kind. It's an I/O device, but where we're headed, and the latest Microsoft device lets you just sort of move naturally and recognizes what your motions are, and puts that into the virtual or augmented worlds that you may be going into. So I agree with that the sensing, computation, communication, actuation, it all just sort of blends into the woodwork, in some cases literally, in this version of the future. So, and you can look at this in kind of the very futuristic kind of stuff. We do have people working on the contact lenses that actually do have display capability. We do have people working on the brain or mind reading helmets that you can just wear. We have people working on putting computation into the fabric that you're wearing on in your clothes. That's sort of far out. But then there's the near-term stuff that if you are a real home automation enthusiast, today, you can have all this stuff that's on the screen there, right? You can have the stuff that is monitoring the temperature and the doors and the lighting and your entertainment system and the windows and everything else, and all that stuff is working wirelessly. It's still in its infancy, but it's all there, and it's right now the user interface to it is very clumsy. It's that thing that you have to pick up on your desktop, but it is in fact there. So what does it take to get from where we are now to where this vision is of this swarm of trillions of connected devices? That non-trivial problem to just provide addresses for them, although that's seemed to have figured that one out with IPv6. But the real issues are that you've got just many orders of magnitude differences in the kinds of requirements that you're making on the communication. For sure, we're going to have high-speed data, latency-sensitive, HDTV streams, and so on. But at the same time, we're going to want to get critical information through from the security system and so on that may be measured in bits per second instead of megabits or gigabits per second. And the importance of the latency and the mobility or the availability of that and the reliability of those streams measured against security and privacy concerns and the complicated by the fact that everything is moving around, those are the real challenges on the communication side. For sure, we're going to need a lot of computational power, but fortunately, I think if you look toward where the molecular computation on square meter fabrics is headed, Jan's picture of the data center is, there's data centers in the wallpaper in every room, and so you've got to figure out how to get that to do what you want it to do with the energy budget that you've got. So how are we going to address these things? Well, we're going to create a playground, and we have the 4th floor of Corey Hall to do it. And the big picture is, it's all about what utility can we deliver, and that's where, again, the 3 talks that you heard this morning, I think, really serve as kind of an underlying motivation. This is the world that we're trying to get to, in where the hardware and the devices side is trying to lead into and feed that vision of what things look like. And so you've got your services and application, but it's the resources that you need to map that into: communication, computation, sensing, actuation, storage, and energy. Energy being the limiting factor for all of them. And then just like Jan talked about the what was it, data center operating system or something like that, it's that same kind of idea, the swarm operating system. Maybe it ends up being exactly the same ideas that come out of that effort, but that idea that you have to have an operating system that works across these distributed devices in your environment, that is extremely dynamic to balance and adapt to the continuously varying demands that are being made on that environment. So, Swarm Lab is going to be our playground in the 4th floor of Corey Hall, and will consist of both sort of or all of the next generation nodes we're going to make, the next generation devices that are being fabricated, electronic, post-silicon, optoelectronic, optical, for doing the computation, communication, storage, energy storage, as well as bits and energy harvesting. And they're all going to be these are all multidisciplinary problems, so they're very multidisciplinary labs and so on. And this is seeded initially by a very generous donation from Qualcomm, which is being announced today. And the reason why we need a very generous donation and why it's just the beginning is that we are trying to redo the entire 4th floor of Corey Hall. Many of you may have put in long hours in the micro lab in that building. So the north side of Corey for the last several decades has been where we've done all of our microfabrication. Now with the new Citrus building, Sutarja Dai Hall, we have the Marvell lab for micro-nano fabrication, and so all of the stuff has now moved out, and we're going to renovate that floor, and there'll be 4 main labs that go in there. There's the post-silicon lab, the nanomechanical lab, the new photonics lab, and then the swarm hive, sort of the ultimate playground for these. And I'll talk a little bit about each one of these. And one of the things that all of these have in common is that they are going to be multidisciplinary. They're going to be open, research centers in the same spirit as the microlab. And there will certainly be dedicated research in each one of them, but each one of them, as it turns out, as the things were kind of coming together, everyone is looking at having a characterization testing facility inside their individual lab and making that open, making that available to other people inside the department, outside the college, and outside the university, both other universities and industrial collaborators. So the success that we had with the microlab of bringing in people from different disciplines, bringing in companies, the Berkeley Microlab Association, and all of the startups and products that came out of that, both from big companies and small, hopefully we'll be able to replicate that with this much more diverse set of fabrication and testing and characterization capabilities. So those labs, starting with post-silicon, so the idea here is that we've got tremendous capabilities in things outside of silicon. Silicon is on its own roadmap, but what can we do beyond that? And the idea is that we can make roll-to-roll processing. So this is Vivek Subramanian is doing inkjet printing and gravure printing of electronics components of all kinds, both electronics, FETs, passives, energy storage, communication, sensors. All of those have been demonstrated to date on roll-to-roll or inkjet kinds of things. Ali Javi is doing transfer of nanowires, various semiconductors and other materials from one fabrication technology onto others and making very high quality devices and putting them on top of plastics, for example. And one example of what he calls XOI, so not silicon on insulator, but whatever. You tell him what you want to have on insulator. In this case, it's indium arsenide, where he's getting spectacular mobilities in these transferred films. And if you look, sort of zoom in on the thin layer that's being transferred on top of the oxide there, you see about a 15 nanometer layer of indium arsenide and actually making real functional FETs in that material. It's just one of many things that he's been able to transfer onto silicon and, in fact, transfer onto a variety of polymers and other things in addition to silicon. So it's not just XOI, it's what he's calling XOY. You pick X and Y and he'll transfer one onto the other. In the nanomechanical lab, this is all about using MEMS and nanotechnology for certainly sensing, actuation as well, and even in some cases computation and communication. That they're very interesting things that you can do with mechanical structures at nano and MEMS kinds of scales. And just one example I'll give, there's a demo of this in the BSAC area after lunch. Ultrasonic range finding. So miniaturizing and making arrays of ultrasonic rangefinders now lets you do sub-millimeter accuracy sensing that will give you 3D images. There's another one of these that is a micro LiDAR, so something around the size of a sugar cube that does the same kind of LiDAR functions that Professor Zakhor was talking about in the previous talk. And doing these at a size and a power scale that allows you, again, to sort of imagine putting them essentially into the wallpaper, that's just a part of the environment that you're in. Of course, it's recognizing your motions. You don't have to carry the Wii remote. The room is figuring out exactly where your fingertips are and where your hands and arms are moving, and can interpret an angry shrug from you as something that should affect the way it's presenting stuff to you. Many of you have probably seen Michel Maharbaz's satanic micro-cyborgs. These things are actually, you literally get to fly them around the room with a joystick. They've got a radio microprocessor and control electrodes inside this thing. And the future of that, I'm working with him to miniaturize all of that so that we can put it on something that is not quite as terrifying as one of these monsters beetles that he's been using. We put it on little house flies and then have that be a part of our repertoire of what we can do with mobile robotics. Take it down even another level. Luke Lee is working on what he calls nanosatellites. These aren't satellites out in space. These are satellites inside your cells. And he can literally drive a little nano robot around inside a cell and drive it up to an interesting thing, part of your cellular structure and make measurements on it today. He's already demonstrated that he can do that. So, we've got this at a variety of scales, from Ron Fearing's things that are in the tens of centimeters to mine in the millimeter to centimeter to bugs to even the nano scale, all a part of this sort of the output side of interacting with our robots. Moving to the new photonics laboratory, incredible things coming out of there. The highest performance, highest efficiency single junction solar cells recently announced, nano lasers and so on from Connie Chang Hasnain's group. The font didn't quite work on this one, sorry. She's showing, you don't have to do X on insulator. You don't have to do it by fabricating separately and transforming. She's actually shown, heck, we can grow gallium arsenide and indium gallium arsenide directly on polycrystalline silicon. And so showing that she can make high efficiency solar cells in the lower left and actually make gallium arsenide, indium gallium arsenide lasers in the upper left, and so on. Some beautiful, beautiful stuff going on there. So, and then finally, the bottom part, the swarm hive. This is kind of Jan's baby and mine as well. Is trying to put all that together. Everybody involved in this fourth floor activity is interested in obviously pushing their own very focused research agendas, but they're also interested in making these capabilities available to others and in packaging them up in ways that are going to allow us to put that into a test area so that we can expose the capabilities to a much broader audience of people, including all of you, of course. And so that's what we're hoping to accomplish with the Hive. And so last two slides, finishing up. So Jan has given me the laws of the swarm, which I guess makes me Moses and makes him, well, anyway. So it is all about connectivity, but it's all about connectivity in the context of energy. It's how do you choose where the computation goes? You can send everything off and use the cloud for computation, but the communication costs you a lot more per bit usually than computation and local storage. So that kind of trade-off is critical. It's all going to need to be adaptive to the demands of the environment, both in terms of the requests for services and capability and in terms of what the environment is providing. Is the sun shining on the wall that happens to have the imaging capability in it that you need or not? And in an ideal world, Jan says no one wins by being selfish, and it'll be very interesting to see in this future society of computation and sensing and communication, whether you end up with electronic dictators that go and try and take over massive parts of the computational fabric and need to be ostracized and dealt with. So anyway, so Dave asked me to put a 2020 vision in here with the almost certainly column. Printed systems, I think, is for sure. This is basically because it's already been done. I think pretty much everything in the almost certainly column I can say is almost certainly because we've more or less already done it. Being able to inkjet print, sensing, computation, communication, and power, demonstrated already. X on insulator and X on Y, that kind of transfer, a lot of things demonstrated there. Efficient solar. Connie and Ming are convinced we'll have photons in every chip in 10 years. It's just it's already happening. I think maybe not no watt unmonitored, but for sure no kilowatt unmonitored. Everything is all the power consumption monitored. Instrumented cities is happening already. Instrumented humans is already happening as well. That's if you read my Life in 2010 predictions that I wrote in 1999. I predicted that in 2020, but was actually contacted a couple of years ago by a company that sells implants, prosthetic implants, and they were saying, we have some customers that have several of these things, and we're thinking it's probably time to network them. So it's already happening. And so finally, if we're lucky, how is this all going to fit into the talks that you heard earlier this morning? It's not about interacting with your device in some sort of clumsy mechanism. It's about feeling like the sensors and actuators and computation and storage around you is just an extension of your natural body and intelligence and so on. So thank you very much for your attention.
where's your house is?
Where's our open house? She's waving a sign. She won't tell. Where? Stanley Hall. There we go.
Apparently, cleverly, the swarm group is using BSAC as the sign for swarm. And then there's the students are waiting to talk to you at open house 2 to 4, right? Is that basically a question?
In the slides you showed of 4th floor, you showed all these other labs that are working on the moats, and we've made a lot of progress on all the moats, and you're citing that here. I really want to know more about the Swarm OS and what the Swarm Lab is going to do to take advantage of these little pieces that we're sort of mastering to get the broad intelligence that only comes with numbers.
Yeah, so Swarm Lab is actually all 4 of the labs. So it's new photonics, nanomechanics, and post-silicon, and the Swarm Hive. And so the Swarm Hive is charged with figuring out how to integrate all of the devices that are coming out of those pieces. I agree with you. The moats are basically done. But it's how do you integrate it all? And that's, that trade-off. This is where there's some creative tension between me and Jan. I'm very much enamored with a small amount of local intelligence to make local optimization decisions, and then centralized intelligence to get you out of local minima and to actually sort of orchestrate the whole thing. Jan is much more of a distributed intelligence, top to bottom kind of guy. So I think we don't know. It's way too early, I think, to say where that's going to go. But those are, that creative tension hopefully will lead us to work hard.
Yeah, well, I'd say what we're trying to do with these events, and we're trying to do every year, is announce brand new ventures. So we're kind of giving you where we're going, and the starting point, and who's involved, and we'd love to have you participate to help us figure out how to get there, as opposed to we know we're going to prove that this is the right answer.
Yeah,
right?
this is one where we definitely do not know what the right answer is yet.
There's a question back there. Bill?
I've got a question about the direction of battery technology. My impression is it's moving very, very slowly generally, though maybe electric cars are going to create some difference in the rate. But what do you see as the rate of improvement, and is what really going to happen that we get just extraordinarily stingy instead?
So battery technology is improving. It's a pretty mature technology. There is still, theoretically something like an order of magnitude left on the table for aluminum fuel cells and fuel air batteries. But basically, I don't know, something like 10% per year is what the number has been on batteries for a long time. The focus that we have is, we're not trying to do anything new with battery energy density. There's a bunch of the labs are working on better ways to create batteries, so inkjet printing of batteries and transfer of batteries and micro batteries and things like that, but using traditional chemistries. But really the work is all about the management of, doing the intelligent sensing, communication, computation, and doing the right trade-offs there. As David likes to say, it's all about doing nothing well, and most of our systems don't do that. Most of our systems burn a lot of power even when they're not doing much. Increasingly, in the last decade, you've seen systems, and certainly in wireless sensor networks, where the idea is you shut things down when they're not doing something. And so they wake up briefly, they send off a packet, or sample something, or receive a packet, and so on. And the energy, the savings, we've gone down from when we first started in the wireless sensor network stuff, we've gone down about 5 orders of magnitude in energy consumption. And 2 orders of magnitude there are the 1.5 to 2 are the radios and the microprocessors themselves, just doing much, much lower energy per operation. And then the other 3 orders of magnitude come from intelligent algorithms. And so there's still, before you hit fundamental limits, there's, I don't know, another 5 orders of magnitude probably on the table. And there's an order of magnitude or 2 that I think we can easily get to in the next decade. And so that's compared to a 10% per year increase in battery storage. It's all about the efficient use of that energy, not about storing more of it.
Okay, we'll start the panel session at 11:30. Thanks very much.